Section 8.3, the integral test. What the integral test is trying to do for us is answer the question, does a series converge? Now, in the previous section, we introduced the idea of an infinite series, and we talked about the fact that when we had a geometric series, and if the absolute value of r was less than 1, we could calculate what a infinite series converged to. The integral test isn't as satisfactory as that. It can only tell us, does it converge? Does a series, infinite series, converge or diverge? That's all it's going to be able to do. Now, how does it work? Well, in fact, if you think about it, there is a lot of similarity between an infinite series and a improper integral. They both kind of deal with things going off to infinity. Let's imagine a function, and in the book this is example 2, where the function is we're summing from n is equal to 1 to infinity of the function 1 over n squared. Okay, and the question is, does this converge? Well, you can look at this and say, well, as n goes to infinity, this goes to 0, so that holds promise that the series converges. Yeah, that's true, but it doesn't prove that it converges. Okay, this could go to 0 as n goes to infinity, and yet the series does not actually converge. So how are we going to go about doing it? Well, first off, let's plot this function, and roughly something like this. And here we have 1, 2, 3, 4, 5, like that. And I'm just going to plot out little kind of Riemann histogram rectangles here. Something, oh God, this looks pretty bad. It's hard to write on this little pad. Something like that. Okay? So there they are. This is the value of the function at 1. So this is going to be 1. If we plug in 2 here, we get 1 over 2 squared, which this is supposed to be 1/4, which obviously it's not from my crummy drawing, but you can imagine. And then if we add up these little rectangles, the base is 1 times the height, but if you added all these up, that's what the partial series up to 5 was. And if we kind of imagine this going out here to infinity, if we sum the area of all these rectangles, we'd wind up with the value for the sum of this infinite series. But you also notice that, hey, we can think about the area under this curve too. Okay? And in particular, let's just say that this first rectangle, this is kind of a special one. Let's just take this out and say, well, what is the area under this rectangle here? Well, that's 1, because that's going to be an interesting one to leave out. So we'll put that there. Plus the area under the curve from 1 to infinity. What's that area going to be? Well, for one thing we know, it's bigger than the sum of this infinite series, because in each case, this area is a little bit bigger by this much, see? So if we said, well, let's just take the area under this curve from 1 to infinity, the improper integral of 1 over n squared dn, if we were to solve this problem and find that it converges, then we know that the infinite series must converge, because all this series has got to sum to less than this, and if this converges, that means this converges. So we can real quick solve this, and we get 1 plus, and the derivative, this is going to be n to the minus 2, take the integral of that, and of course that's going to be equal to minus n minus 1, so that's equal to just 1 over n minus 1 over n. Now we need to evaluate that from 1 to infinity, At infinity, obviously this goes to 0, so we simply get this is equal to a minus minus 1 or equal to 1. And then we come back and add that original 1 that came from this up here. Remember that? And we get that the area under this curve here from 1 to infinity is 1, and then we add in this little 1, and we come up with the answer of 2. Now what does that represent? In a way, it doesn't represent anything in particular. It is an upward bound. We know that this sum converges, and we know that it converges to a number that is less than 2, but we don't know what that number is. We know it converges. It's going to converge to a number that's less than 2, but we don't know what it is. And in the book they point out that the actual convergence is pi squared divided by 6, which is equal to 1.644. So you can see, yes, indeed, it's smaller than this, but this value did not very accurately tell us what this series did converge to. It just told us that it was going to converge. Okay, now the question then arises, when can we use the integral test? The integral test can be used when we have a continuous, positive, and decreasing function. Okay, continuous, positive, and decreasing. Now, so, in fact, that little example I just had was a good one. Asymptotic approach to 0, that qualifies. But if, on the other hand, it had looked like this wouldn't qualify because it's not uniformly decreasing. And this one wouldn't qualify because it goes negative, etc. So we've got to have the special case where it's continuous, it's positive, and it's decreasing. So what will happen is, in a real-life situation, you're going to have to test and prove, using your calculus skills, that the function is indeed continuous, positive, and decreasing. The positive part you might want to look at for the range, what's the maximum and minimum area, this, that, and the other. Is it decreasing? You want to take the derivative and find, is the derivative from 1 to infinity always negative? If it is always negative, or negative or 0, then you know that it is a decreasing function. And that's what you're going to have to do. So not only do you have to be able to apply the test, but before you actually plug in and solve one of these things, you have to come down here and prove it's continuous, it's positive, and it's decreasing throughout.